Hey physicists, I hope that the Ohm's Law lab went well for you. I just wanted to do some follow-up, figured I would put it on a video so that either way, whether you got it done in class or not, you could get the information that you needed. So you did your Ohm's Law lab, and when you were doing the lab, just to recap and make sure that we're on the same page, you measured some voltages, and then you measured the corresponding currents for those. And then I asked you to graph them. So hopefully you put voltage over on the y-axis and you put current on the x-axis. And then my hope for you, and if you were doing things right and everything got measured correctly, then hopefully for each of your three resistors, you got a straight line. So hopefully you had something that maybe looked like this. And these are just kind of, made up points, obviously, but kind of this sort of thing. So using our physics knowledge and using our understanding of how graphs work, we can see that we've got something that looks like a y equals mx plus b. We've got something that looks like a straight line. We know that the y is your voltage, and we know that your x is current, and there's something there, some constant of proportionality, right? That is the slope of our line, and that is the thing that I want to focus on here today for a couple of minutes. And that thing, that unknown value that we haven't really talked about yet, is resistance. So we've talked about it a little tiny bit in that we've mentioned resistors, right? But what exactly is resistance? That's what we want to talk about right now. So resistance is the opposition that a wire, oh my goodness, or a device provides to the flow of electrons in a circuit. Okay, so the amount of resistance that something has, that a device has or a resistor has or whatever, is dependent on a few things. So if you think about all of those little resistors that we had, they all look just about the same. It's hard to believe that they might have been orders of magnitude different in the resistance. And so one of those things that resistance is dependent on, so we'll say depends on three things. One of them is the material. So each of those resistors that we had that we were doing our lab with was made of a different material, and the material was different and had a different resistance. And in fact, the resistance was dependent on what we call its resistivity. This is one of those words that AP Physics 1 College Board people point out in particular that they want you to know, which is why I want to make sure that we spend a little time on it. So resistivity is marked with the letter rho, okay? Welcome to another Greek letter, the letter rho, it's little rho, okay? And basically it's just how well do electrons flow through it, okay? So it's kind of related to whether it's a good conductor or not, but there's a little bit more to it. The thing that I need you to know is that it's dependent on the material, and as the resistivity increases, so does the resistance of the resistor. So resistance, by the way, is marked with the letter R. Okay, so the material is one of the things that resistance is dependent on. Another thing that resistance is dependent on is the size of the resistor, and that comes in kind of two flavors. The first of those is the length of the resistor, and this you can think about like in terms of the length of a wire, right? So copper wires have a very, very low resistance, and generally in a circuit that has resistors on it, the resistance of the wire itself is minimal. But if you are going to become an electrical engineer, you will discover very quickly that having more wire gives you more resistance. The length of the wire, as the length increases, the resistance of that resistor or of that wire increases. That kind of makes sense. The further you have to go through a little tiny narrow space, for example, for electrons, the harder it's going to be for those electrons to get through. And then the third thing, also related to size, is the cross-sectional area. So you can think about this like a very, very narrow pipe versus a wide pipe. The bigger the cross-sectional area, so we have a little tiny narrow pipe versus a very, very big pipe, as the cross-sectional area increases, it may make sense then that the resistance actually decreases, right? You have a wider pipe, that means more electrons are able to get through per time. The resistance then goes down. So we can put these three things together and we get an equation for the resistance of a material. So again, as resistivity goes up, resistance goes up. As length goes up, resistance goes up. And as cross-sectional area goes up, resistance goes down. So this is the little piece that tells us how resistance is dependent on the type and the shape of material that it is given. So that is what resistance is, and that's kind of how it fits in to this equation here. So now we're going to look more specifically at that equation. Okay, so I'm going to write this equation down here again, but I'm going to write it down in a little bit of a different format. I'm going to introduce you to it by name, and the name of that rule or that law is Ohm's law. And Ohm's law is a law of cause and effect. And before I actually throw Ohm's law up on the board here, I want to have you remember another cause and effect law that we looked at so long ago. So I'm just a little thought bubble over here just to remind us of everybody's favorite, or maybe not your favorite because there are a lot of good ones, but a pretty great one, Newton's first and second law. You'll recall that Newton's first and second law, we say is A is equal to F net over M. And I don't know if you remember, but when we first started defining this, I insisted that we write it this way because it's also a cause and effect rule. Okay, so the acceleration of an object is dependent or is a result of a net force acting on an object with mass. The higher the mass, the lower the acceleration. The higher the net force, the lower the acceleration. But both of those things, the net force and the mass, are the causes or the things that dictate the acceleration that happens. Ohm's law is exactly the same. It's the same kind of law. So in the same way, the current is determined or is the result of a voltage being applied over a material with a resistance. So if we think about it in the same way that we had, okay, the current is a result of a voltage being applied over a resistance, okay? This right here is Ohm's law. This is the one that you graphed in your lab, and this is kind of the big rule for circuits. Now, I have to give you one little heads up on this, okay? And this is one that I honestly learned the hard way, okay? This law here, unlike Newton's first and second law, is not universal. Newton's first and second law always, always, always is true. Ohm's law is only true for what we call ohmic devices. Okay? Ohmic devices are things that follow Ohm's law. It's kind of a circular definition, but the rule is these ohmic devices are ones in which the resistance is not dependent on temperature or other outside factors. So the funny story is that when I was in graduate school and I was doing my student teaching, I was like, oh, let's do Ohm's law. It'll be so exciting. And so I did this whole lab, almost exactly the same lab that you guys did, except that instead of using resistors, I used light bulbs. Problem was that as light bulbs heat up, their resistance actually changes. And so instead of getting a nice line like you did, all of my students got these funny curves. And I was like, what is going on? And then I went home that night and I was like, oh, that was what it was, because for a light bulb, the resistance changes as it heats up. So remember, please, so that you don't make the same mistake I did, that Ohm's law is only true for ohmic devices. Now, just fun fact here, I guess not fun fact, just kind of obvious, but so that you're not scared of it another time, devices that don't follow Ohm's law they are called, are you ready for this? Hold on to your hat. It's pretty wild. They are called non-ohmic. I know, right? That probably blew your mind. Probably enough for your information for today. Have a great day.